Ladies and gentlemen, one of the defining features of India Space Congress has always been its commitment to fostering research, innovation, and thought leadership across the global space community. This year, the global call for papers attracted an overwhelming response from researchers, academicians, industry professionals, and students, reflecting the growing depth and diversity of ideas emerging from the space ecosystem. Following a rigorous evaluation process conducted by an esteemed jury panel, the submissions were assessed on the basis of originality, technical merit, innovation, relevance, and potential impact. Before we announce the winning papers, we would like to begin with the Special Recognition Award. This special recognition acknowledges a noteworthy research contribution that stood out for its relevance, technical depth, and potential significance to the future of the space sector. In recognition of their outstanding contributions, SIA-INDIA is pleased to award cash prizes to the winning papers, in addition to certificates of achievement and recognition from India Space Congress 2026. To present this Special Recognition Award, may I invite Mr. Anil Prakash, Director General, SIA-INDIA, to kindly join us on stage. The Special Recognition Award is presented to Mr. Balakrishna Tarihal and his co-authors for their paper, Quantum Machine Learning for Space Data Analysis, Bridging Quantum Circuits and Satellite Communication. Many congratulations to the author for this remarkable contribution. Thank you, sir. We now move on to the award-winning papers of the ISC 2026 Global Call for Papers. The third prize is awarded to Mr. Priyesh Kumar Jain and his co-authors for their papers, Development of a Resistive Grid-Based On-Orbit MMOD Impact Detection System. Congratulations to the team. Moving on to the second position, the second prize is awarded to Mr. Ashutosh Kumar Jha and his co-authors for their paper, DebriSat, a lidar-based nanosatellite for autonomous space debris detection, classification and collision avoidance in low Earth orbit. Please join me in congratulating the authors on this outstanding achievement. Thank you. And now the first position. The first prize is awarded to Mr. Ashutosh Kantagharia and his co-authors for their paper, TerraVilio, a 12U CubeSat architecture for multi-gas point source atmospheric attribution at 117 meter, GSD using Vilio optics, UV, VIS, DOAS, and on-orbit edge AI. Please join me in congratulating the authors on this outstanding achievement. A well-deserved recognition for an exceptional piece of research. Congratulations to the winning team. Ladies and gentlemen, a round of applause for all our Global Call Papers awardees. As part of their recognition, thank you, sir. As part of the recognition, we are pleased to invite the authors of the top 2 papers to share their research with us. May I first invite Mr. Ashutosh Kumar Jha, representing the second prize winning paper, to deliver his presentation.
Yeah, I'm just. So, very good evening, all of you guys. My name is Ashutosh Kumar Jha from the final year student from lovely Professional University, and together with my co-presenter, Pawan Kumar. So, we are here to introduce DebrisSat. It is a nano satellite concept that can autonomously detect and avoid debris, space debris, without waiting for instruction and from a grounds. So let me start and explaining why this problem is urgent and why this is important in terms of space debris. So right now in low Earth orbits, where most satellite operates, over has 27,000 tracked objects and more than 5 lakhs untracked fragments between 1 and 10 centimeters in size. A small piece of metal is orbital speeds of 7 kilometers per second carry enough energy to completely destroy a satellite, and it can make major problems in space. So this can trigger what is called the Kessler syndrome. We know this, and it's like one collision causes more debris, which causes more collisions, eventually making entire orbital zone unusable. So the second big problem today's ground-based radar system takes 20 minutes to detect the threats, and it sends a response by then. So it is already too late, we can say. So So yeah, so after that, I will just would like to explain the research gap and the mission objectives to find this problem. So yeah, after reviewing some of the papers that is related to the debris management system and detecting and classification of debris within the LEO, so we found one clear gap. So no system today combine onboard LiDAR sensing and AI-based classification and autonomous avoidance on a single small satellite. And debris is designed to, our DebrisSat is designed to fill this gap. So these are work on the 4 objectives and 4 steps. The one detects any object within 180 meters of the satellite continuously. And the second is to classify the objects in a LEO with the active, non-actives, debris body, and some asteroids. And the third is to calculate collision probability under the 50 milliseconds. And the last one is either dogs and objects autonomously or alerts a human operates with camera images for verification after the detection of LiDAR. So after, I would just, I would like to just explain our DebrisSat system architectures. So it's a 6U CubeSat, roughly the size of shoebox, designed to fly in a 500 to 600 kilometers polar orbits on a most congested, you can say, very high numbers of debris at that polar orbits, debris zone in the space. The system works as a chain. The LiDAR cluster scan the surrounding areas and send raw data to Jetson Nano, and it's a compact but powerful AI processor. Onboard AI processor module is available at that. So, which identify what is nearby, that decision and then goes to our microcontrollers, which acts as a movement brains, and it fires thruster or reaction wheel to dogs, and also handles communication back to the grounds. So after that, I would just go with the our sensing the computing hardware and system. Okay. Yeah. So I would like just to start every components on debris site is of the self commercial parts which keep the total weights under the 10 kg and the cost affordables. The main sensor are 6 ladders. It's a cluster of ladders, so it can cover the 360 view of the environments nearby them. So it's cover all the 360, yeah. And it's just 2 centimeter accuracy. The second sensor we have used to differentiate light wavelength to detect the material and object is made to aluminums, thermal blankets, so on, helping the system tell apart and active satellites from debris. And our AI, onboard AI computers is processing and the microcontroller satellite movement with the less then it will take the less than 1 millisecond time error, and the UHF communication models send alert back to the ground station. And now I will now hand over my colleagues Pawan Kumar, so he will talk about the AI architecture. Yeah, we can just.
Hello, thank you, Ashutosh. From here, I will explain. Okay, this is the architecture which we have researched, and it's a nano satellite with 6 sensors and 1 camera, and Jetson Nano uh, TNC 4.1, which they are used for AI automation and the movement. So, okay, coming to the software part, here, uh, we have introduced the efficient net and efficient det, um, which is which is a CNN family. These are launched by the Google and which is efficient for the solar. So when the 6 lidars which moves. Okay. Okay, the 6 lidars fires 1000 times per second and send back the raw data, and which makes Jetson Nano create an image which is 3D point cloud, and this image will be detected by the efficient date in a bound box. Bound box is nothing, it is a image, it's a location in the image, and the next thing it sends to the efficient net D4, which is used to classify into 4 things, that is active satellite and defunct satellite and rocket body and debris. After classification, there is a system we have researched is autonomous collisions. So if the AA is 80% above, if it is correct, then it is it says to sorry. If 80% is confident, then it says satellite to move to another direction. Okay. Okay, if 80% more, it will be change the other path. If it is less, and take the camera detection and comes to the end. And dataset simulation, this dataset took from the Spark dataset, where which is not a real LiDAR data. We just made this data from Spark dataset from 2021 and 2022. And we got this accuracy 91.7% calculation. So, simulation. The more safety critical number is the false threat rate of 10 the AM mistaken, which is 2.36, like active and this thing. And the full software calculation will happen in the 47 milliseconds, which is our less than 60, less than 200, which is our budget. So which is good for which is good than the ground station, which is faster 25,000 x faster than the ground station.
Then classification, the limitation and future technology. So I just take. So limitation and future technology is to we believe in the honest about what a system can do, and in conclusion, I would just like to say, to David had proved that multispectral ladder and on-boards AI classification and its work together, and if it can distinguish objects by the shape and tumble, it will be the beneficial for the space industry, and it represents a viable technology demonstration concept that can support and pace agencies and commercial satellite operators, and so that's, thank you.
Thank you for that insightful presentation. May I now invite Mr. Ashutosh Ghandagaria, representing the first prize winning paper, to present the winning research.
Good morning. I am Ashutosh Gantagaria, and along with me I have Om Shakti Swarup Swami and Omkar Anshuman Panda. And we will be presenting our research paper, TerraView, a proposed satellite that not only detects pollution, but also does facility level attribution, and that too at a fraction of the cost of traditional satellites. Current atmospheric monitoring systems, such as Sentinel-5P, have kilometer scale resolution. A single pixel can contain multiple factories, power plants, industrial complexes, and transportation corridors. While emissions can be detected, accurate source attribution remains difficult. TerraView addresses this gap. Our proposed system is a 12-view CubeSat operating in a very low Earth orbit at approximately 300 kilometers. By leveraging VLEO geometry, multispectral imaging, dual gas spectroscopy, onboard edge AI, and low latency communication, TerraView achieves facility level atmospheric intelligence with a GSD of approximately 117 meters. Today, we will present how the system works, how it achieves near real-time emissions attribution, and the commercial opportunities it unlocks. The question is, how do you actually engineer a satellite to survive at 300 kilometers? Over to Shakti.
Thank you, Ashutosh. As Ashutosh noted, bridging the gap between kilometer scale resolution gap to precise facility level tracking isn't just about operational goal. It's a rigid mathematical constraint. To make 117-meter ground sample distance possible, physically and financially viable, we had to completely re-engineer the traditional satellite's optical geometry. The key enabler here is very low Earth orbit. Why can't existing satellites just use better optics? Absolutely, they can. But at 600 kilometers, achieving that 117-meter ground sample distance would require them a custom 30-millimeter lens on a large satellite bus. You end up building one large satellite at the cost of revisit rate measured in days. So that's not real time. We drop that to 300 kilometers altitude. Our strand range halves. The required focal length drops to 15 millimeters. An off-the-shelf C-mount objective fitting inside one unit. This geometric reduction completely unlocks our development model. At the equivalent cost of one conventional satellite, you can deploy 50 plus 12-view CubeSats at a Walker constellation at a 53-degree inclination. This spatial resolution replaces a single slow platform with high frequency continuous repeat rate capabilities. Very low Earth orbit doesn't just make the optics cheaper, it makes the business model possible. But 300 kilometers is hostile. Atomic oxygen and thermospheric drag. These are the main constraints that traditional satellite cannot survive or operate there. But TerraVilio is engineered to survive here. First, aerodynamics and material defense. We fly narrow face forward with 70% of our mass concentrated forward of our center of geometry. This lawn dart effect configuration provides massive aerodynamic stability without burning reaction wheel momentum. To directly mitigate the highly corrosive environment, the forward ram is reinforced with atomic oxygen resistant protective coating, shielding the leading surface from metal erosion. Second, drag makeup. We use unpressurized iodine electric thrusters, which perfectly matches our 0.1 millinewton drag load. Third, power. The thruster needs 70, the payload needs 50. And our peak generation is 105 watts. We solve this using strict time inhibition duty cycle. Observation orbit, run the payload, alternate orbit, shuts the payload down, and fire off the thruster for station keeping. This architecture guarantees longitudinal of mission life. So let's focus on the payload part. Inside that surviving architecture, there is one single unit Nadir belly mount housing 3 instruments. The primary imager. The primary imager uses 5-band very near infrared assembly. The 440 nanometer band isolates nitrogen dioxide via DOS. The 470 and 550 nanometer channels give us aerosol optical depth for PM modeling, while red and near infrared bands compute NDVI for agricultural monitoring and intelligence. A secondary UV detector targets 312 to 326 nanometer range to retrieve SO2. This specifically catches the vessels burning SO2 high sulfur fuel under Maripol on Annex 6, something that no commercial CubeSat currently does. Finally, a thermal microbolometer. When a thermal anomaly from an industrial furnace perfectly aligns with our nitrogen dioxide spike, the attribution becomes legally undeniable. This is the difference between satellite data and satellite evidence. This is the TerraVilio architecture, a 12-unit CubeSat operating at 300 kilometers orbit, delivering facility level intelligence from an orbit no competitor currently sustain. The hardware architecture is secured. To explain how they process the massive optical data pipeline, I will hand over to our Edge AI lead Omkar.
The hardware handles a 40 megabyte multispectral cube every pass. Our 651 kilobits per second. Our effective expand range after FEC raw leaks takes 491 seconds, but our overpass window is merely 380 seconds. The physics denies it, so we built something that can make it possible. Our 800 to 1 compression entirely on board in under 750 milliseconds. 4 DSP stages clean the raw cube radiometric correction strips, geothermal noise, spectral unmixing separates the 5 interleaved bands, geometric correction maps the 234 kilometer swath to ground, and jitter correction frequency domain phase correlation is the final gate. Nothing runs until subfictional motion is removed. Then 3 interference strips fire in parallel on the Ampere GPU. Tensor RT INT8 handles the DOS NO2 retrieval, aerosol optical depth for PM, and NDVI. This is the 750 milliseconds critical path. A CUDA kernel feeds the SO2 UV spectrum in 100 milliseconds and LWIR thermal anomaly detection in 30. 50 milliseconds of UART hands off to the IOBC 40 megabytes into 60 kilobytes in 50 milliseconds inside the budget. The jetson is electrically isolated from ADCS and propulsion. A single event offset touches only the telemetry stream. The satellites keep flying. The three-layer protects the data radiation, hardened EFRAM stores the model weight and reloads. Then on any anomaly, a hardware watchdog restarts the Jetson in 5 seconds. HSA 2256 on the IOBC resets every corrupted packet before queuing. A verified geo-referenced emission signal attributed to specific facility reaches a customer API within 7.5 seconds of overpass. No government system, no commercial system, nothing else is close.
Thanks, Omkar. The final stage of TerraView is communications and delivery. Processed intelligence packets are transmitted through S-band communications and can be relayed through inter-satellite links across the constellation. This architecture minimizes latency and enables rapid delivery of actionable intelligence. To scale this capability further globally, TerraView is deployed as a worker constellation at 53 degrees inclination. This places our coverage band across the world's major industrial and agricultural corridors: North America, Europe, East and South Asia, and Russia, while avoiding the empty polar regions, ensuring high revisit rates exactly where they matter the most commercially. The resulting applications include quantitative economic intelligence, maritime sulfur emission enforcement, carbon market verification, industrial emissions and CBAM compliance. To conclude, current systems detect emissions. TerraView identifies the emitter. Current systems deliver images. TerraView delivers intelligence. By combining TerraView optics, onboard edge AI, and low latency communications, TerraView establishes a new paradigm for facility level atmospheric monitoring. The data exists in the atmosphere. We are simply making it undeniable. Thanks.
Thank you for that excellent presentation, and congratulations once again to all our awardees. We now turn our attention to innovators, entrepreneurs, and visionaries of tomorrow through the ISC 2026 Ideathon Ideation Talent. The Ideation Challenge was conceived to encourage participants to develop bold, practical, and impactful solutions for the future of the space sector. After careful evaluation by the jury, we are pleased to recognize the teams that distinguished themselves through innovation, feasibility, and potential impact. May I request Mr. Anil Prakash and jury member Dr. Upasana Das Gupta, Assistant Professor, OP Jindal University, to please come on stage. The second prize goes to Astrophagus. The team, if you could please come on stage. Team Astrophagus. Can we have a round of applause, please? Please wait. Thank you. And now the winners, Team Andromeda. Andromeda, Team Andromeda. Congratulations to the team for presenting an idea that truly embodies innovation and the future of India's space ecosystem. I would now like to invite Mr. Anil Prakash for the closing address. Thank you.
Thank you very much for your patient, audience and staying back till last event. Now that we have come to the finale of the 3-day, fifth India Space Congress, and the deliberations have been captured. Now we're going to coming out with the recommendations and the conference report shortly. And also we have some of the, we also be submitting the evaluation form to each participant. So we'd like to have your sincere feedback and how we can improve upon, or also what are the industry asks us there. So we can also collate that and also make a set of recommendation. So now it's my honor and duty to thank each and everyone who's here in the hall and also who are not in the hall, because I know it's a very intense 3-day things, and thank you very much for staying back, and also 3-day you have had a full confidence in us, and that shows your presence from since morning to, excuse me, no noise please. So that is the thing, and so we are an industry body, industry association, and we live with your with your expectation. I think we need to work with you closely. We are coming out various programs in future where we will be interacting with you in different form, I think, and as we know, we will also help the industry on the various go-to-market strategy, in which we also helping out them. Now, this is thanks my partners and also the sporting organization, the government organization, who have really has shown confidence in us, and they will become a part of us, our knowledge partner, our media partner. Thank you very much for this. Now this is time to invite those who have worked behind the screen, our SIA-INDIA team. So I would like to invite each one of us to come on stage, so at least you see who the people on the success of this 3-day event. Let me call my team over here. Please come and join us on dais. Each one even. Yeah, please come. And also I would like to call upon also our trusted partners, SP Singh and also Rahul, call to also be available to come and group photograph. Let's give a big round of applause. This is the team who has worked tirelessly to make this event successful. Those who want to use the stage, our photographer, Mr. Sadi, will be available for another five minutes. Those who wanted to use the stage, winners of the call for papers as well as the ideathons, so they can come in a team or group, whatever they want. Please use the stage for photograph.